So we are recording. Okay, great. So welcome everybody to officially the last seminar of this season. So from next week, we take a summer break. And our last speaker for this session is Fabien Alet, who will tell us about probing MBL in 2D disordered constraint systems. So Fabien, please go ahead.
So thank you very much. Thank you, Zarko. Thank you, Akilas, as well, for giving me the opportunity to talk with you. I know many of you here around, and I'm happy to talk about some work which is not so recent, even though it has been published recently, which is our attempts at trying to see if MBL, we could say something about MBL in 2 dimensions. So this is a work done in collaboration with students, Hugo Tevnio, Gabriel Meyer in Toulouse. The second part will be with Francesca Pietracaprina, who was a postdoc in Toulouse. And part of the work, the first part has been done with Ziao Lan, which some of you know, because it was a postdoc with Stephen and Juan some years ago in Nottingham. And I should also acknowledge that actually some of the ideas, the original ideas, were discussed with Stephen and Juan many years ago. So the idea of this talk, first, I shall say that you can interrupt me anytime for any questions. Even I hope I will be able to see questions in Zoom. So if you just want to sleep for the rest of my talk, here is essentially what I'm going to say. So I will try to explore the phenomenon of many body localization in a 2D constraint model, which is called a dimer model, 2 types of lattices. And I will try to do that with exact numerics, no approximation, apart from fine size effects. There are specific aspects of these models, which are different from the, let's say, more standard spin or bosonic type of models that very often we try to discuss MBL on. And what we find, the outcome is that from what we see within the system size and the time scale that we can probe, we see appearance of many body localization. The level of numerical evidence, at least I would like to argue, and that we'll discuss in the end with a critical discussion, is pretty close to what we have for the standard models of MBL in 1 dimension. This is, of course, not a proof of many body localization, but I would like to argue this is the best we can do with exact no approximation numerics. One of the points is that of these models, there are several specific aspects, which I will discuss, but one of the points is that we can explore several lattice sizes and not just 2, if you want, if you do the same thing for spin models. Of course, that doesn't prevent fine size scaling to be difficult. Okay, so let me, I think for this audience, I don't need to recall really what we know, what is many body localization. So I will just jump straight to what is the main question of this talk, which is whether the phenomenon of MBL, which most of the people would argue is happening in 1 dimension in lattice model for strong enough disorder, whether it can happen in larger dimension. And usually the first answer that came historically is that it's an argument more than an exact answer, is that it should not happen because of this phenomenon which I've tried to describe here. So let's imagine we have a sample which is many body localized in 2 dimension or dimension D, let's say, which is would be the blue sample here. And technically, people assume that there are local integral motions to describe MBL in the full blue sample. And let's imagine that we initiate some ergodic bubble, something which is not localized, some kind of more ergodic part here, and try to discuss whether this would be able, because there are interactions, be able to summarize some region around that and see eventually if this buffer region, which is summarized by the red bubble, is large enough. So the argument goes this way. Basically, you have a competition between level spacing, which induced by disorder favors MBL, and it's scaled this way. This is rho is the density of states. So let's imagine we have a spin system with 2 degrees of freedom per spin. or two values. This is going to be the scaling of the level spacing. It's exponentially small, exponentially with the volume. And you can then, the comparison has to be made with the matrix element because interactions, they favor summarization, which is a standard way of seeing serialization through the ETH. And if you do the computation, assuming short range interaction, you have a square root of 4, which happens here. And if you do the math, it's kind of easy to see that only in one dimension there's a true competition. Otherwise, the matrix element will always win, which means that the MBL is unstable and the red region will actually create an orange region, a summarized bubble, summarized part, which will actually be the full sample. So of course, this is just an argument, it's asymptotic, there's no question of time scales here. It does not that precludes the fact that MBL could be a transient for a very large time, but okay, that's the main argument due to these authors. Nevertheless, people try to say something more precise and try to study lattice models of MBL because we like to do that, and we, in some cases, we can do it. It's very difficult in 2 dimensions for many reasons, but there have been some nice works. So some of these works are a bit slightly older, but I think they are really nice. Most of them assume some kind of variational computation, either assuming a low entanglement entropy of the eigenstate, or assuming that the phase is localized and to see or at large disorder and trying to see up to which low value of disorder the system can stay localized. So there's been some unitary transform work, very nice by Thompson and Shiro, some very complex tensor network calculation on lattice sizes, which have about 100 sites for different models. There are some approximate diagonalization scheme, and all of this seem to say that for large enough disorder, it seems that the MBL is there. Of course, these works are slightly biased towards MBL, and most of them cannot describe a fully thermal ETH phase, even though there are some results here for this second paper. But still, it seems to say something, which is in contradiction with the previous argument. On the next slide, I will also show some even more recent results. Two of them, at least one of them, which I like very much, and the other one, which I haven't time to analyze yet. But the first one is this nice work in the group of Ryan Clark, where they are able to build some approximate local integral of motion in 1D, 2D, and 3D using some involved scheme where you develop an initial ansatz for the local integral of motion in terms of local operators like this, and you look at how many of them do you need, and then you check if it's a good local integral of motion by computing the norm of the commutator. And they find for large enough disorder for various models actually pretty good local integral of motions. And they do several tests, and it seems to be kind of meaningful. There's also this QMC work more recently, which also finds the MBL in 2D Heisenberg plus random field. So the numerics, some numerics seem to find some traces of MBL, even though it's very hard, as we will see soon, to do exact numerics. In 2D, there seems to be some indication. On the other hand, there have been other types of numerics, in that case, dynamical simulation with a time-dependent rational principle, which done by Elmar Dogen in this group, which try to, they also locate some kind of ETH to MBL transition in the dynamics, but they try to look all the critical disorder scales with system size. And what they find, it's a hardcore boson model on the potential, that the critical disorders seem to scale more or less linearly with the system size, which would mean that in the thermodynamic limits there is no MBL in the long time limits. Okay, so this is obviously a very difficult challenge for theory. We will try to say a few words about that in a specific model. But to finish the introduction, I would like to recall that cold atom experiment, either for bosonic model, like in this quantum microscope setup, in the group of Emmanuel Bloch. Also, this is fermionic atoms in a 2D quadrupedal potential in the same group, but it's a different experiment. All of them see hints of localization, at least slow dynamics, up to fairly long time scales in 2D for large enough disorders. So obviously, it's still an open question, and it's not clear in which direction, and if we are able to say something very firm. But nevertheless, I think it's really an open question that needs to be addressed as best as we can. So before I jump into the model, is there any, if you have any question about this very rapid summary of 2D works? Maybe there have been actually other works which I'm not aware of. Some of you were perhaps involved in that, but that's more or less the status that I see, that actually many numerics find MBL, even though they have a hard time finding the ETH phase in 2 dimension, and at least in the same model. No questions?
Maybe can you go back one slide?
Yeah.
So can you explain a bit more this on the left, the construction of the commutators, local interval? So what exactly did they do there?
Okay, let me try to recall. I think they just expand some hypothetical local integral of motion, which they call τIz, into a poly string, which is form of things. And they just have a minimization goal, minimization of that. So you can expand this τIz in terms of all the poly matrices in some finite regional space, which they some finite bases, and then they expand the bases. At some point, they see some convergence, and they try to minimize. So the optimization goal for the parameter of expansion is to minimize this, and they also want to have some binary operators. That is to say, the τIz must have eigenvalue plus or minus 1. They also import energetically, if you want the minimization, they also try to minimize that, and they find at large enough disorder that the τIz are well localized. I mean, this is an example. I don't know. I think in 2D, so they go to 21 by 21 lattice, but they find local integrals of motions which are actually around 2 or 3 lattice sites, like that. So they assume that the expansion is well converged, and this is a norm. This is the norm of the commutator, and they get pretty low values, right? So that, to compare, for instance, to other things.
And do they actually show that there's like extensively many of these operators?
They know that I think they actually can only construct one for each disorder sample. Whereas you're absolutely right, in this work by Thorsten Wall, they actually construct
yeah, there they construct everything, the whole
unit. Yeah, the full unitary. Here they only have a limited number, but they find it systematically, I think, and consistently. Yes, and it's really local and so on. So yeah, actually, I realized that this paper did really a nice work on you recently. But that's something interesting. In the model I will be discussing, is that okay? Yeah. I will not be able to construct local integral of motions, and you will soon know why. But nevertheless, I will pretend that I have signs of localization. Okay, the model. I know that many of you, one is an expert, Ioannis as well, and I think Achilles also know this kind of stuff. We have models which have some specific aspects, in the sense that Hilbert space of this quantum model are not tensor products, and that's what I call constraint model. And the one I will be discussing is a dimer model. It is celebrated in statistical mechanics for many reasons. It are actually reasons in the 30s, like almost 100 years ago, in absorption physics, mathematical physics. Also, the quantum dimer model was introduced in the context of ITC superconductivity. But here we will use it to do some for 2 reasons essentially, which I will discuss now. We will try to use it to do MBL. So the model is as follows. There is a constraint that you take a lattice, and every lattice site must be touched by only one dimer, which is this orange type of stuff. So every dimer touches two nearest neighbor sites. It's a constrained configuration space. It's not a tensor product. And even though in the end it might play no role, at least from a theoretical point of view, it's one interesting aspect is that there is no simple way of writing a local integral of motions for this model, because you cannot build, at least I think, you cannot build a local basis which is of operators, which covers the full operator space. So that's one technical reason. The other technical reason is the following. So let's imagine we would like to study spin chains, or spin in 2 dimensions, spin models, even with spin and one half, the Hilbert space could still scale like 2 to the n, whereas the number of sites, whereas we know very well that this kind of constraint makes the Hilbert space size scaling much smaller. So it's just a numerical factor, but it's an exponential. It's kind of useful, right? Especially for the honeycomb. Another aspect of this model, which I should be talking about, is about symmetries. So I will be talking about square lattice and honeycomb lattice, and most of them, if you consider dimer coverings of these lattices, they have a conserved quantity, which is called the winding number. So basically, you just draw a line. Is in one of you have 2 choices in 2 directions, and you just count algebraically the one which go from left to right with this A to B, if you want bipartiteness aspect, in such a way that here you would count -1 because you go 1 time to the right and 1 to the left, and here only 1 to the left, that makes -1. And if you repeat the calculation at every line in this direction, it will always be -1, which is why it's a conserved number. There are 2 conserved numbers, and it actually means there's a U1 symmetry in this model, which we know is compatible with MBL. So in principle, there's no obstruction to MBL. We will use that sector in the rest. Another aspect which I will be discussing is that we can play with this in 2D, we can play with different types of lattices in order to have larger strength. So far for the Hilbert space. So the model in itself is very simple. So you have a dimer covering like this one here on the square lattice, or this one on the honeycomb, and you have to use the Hamiltonian that we will be considering. It's just playing with these dimer coverings in 2 different ways. One with a kinetic term, which is described pictorially like that. So if I do a drawing, it means I can flip. This is a kinetic term. I can go from one configuration to another in this Hilbert space like that. And the kinetic term on the honeycomb lattice is involving 3 dimers around flippable, so-called flippable packet, like this. So this is a standard model for quantum dimer models. You have a kinetic term and you have a potential term, which just counts diagonally, if you want, as a number of flippable packets. And the aspects which will be different. For instance, I know that Johannes has studied a lot these models. One aspect which, for the ground state physics, one aspect which will be different is that we will use these models, introduce some disorder. Disorder will be as a random potential, exactly like a random magnetic field for the standard model of MBL in 1 dimension. And we will study highly excited states, not ground state physics. So what can we expect? So we will scale the disorder in this way. We'll take a uniform distribution between -V and V, and we will try to draw hypothetically this phase diagram as a function of disorder, assuming that the kinetic energy is scaled to 1. We know that if there is no disorder, that's a nice work by Xiao and Stephen, there's ETH. Even though it's a constrained model, you can show that there is a ETH which is valid. So we kind of guess, maybe what we hope, that if the disorder is strong enough, the system will many-body organize. There are connections and specific aspects of this model to look for MBL. As I said, there's no tensor product, there's no obvious construction of local integral of motion. Also, quite important, there's no free particle point. There's no limit where the interactions go to 0. There's no Anderson localization possible. there's no limit where there is low Anderson localization, which does not allow us an opportunity to try to find this limit. The dimer constraint, if you think about it, it just goes slow. And actually, it's a U1 symmetry, so it's a natural connection to U1 gauge theory. And there have been many works talking about localization in this type of gauge theory without disorder mostly. Also, the final point is that if you just forget about the kinetic term and just look at the strong disorder limit, there are actually many degeneracies. There's no obvious, it's a nice stat-leg model, which I was actually not able to solve in the strong disorder limits. There are many funny degeneracies. Okay, so unless there are some urgent questions, let me try to show you what we obtained on this model, in particular trying to find the excited state and properties of this model. Shall I go on? Just interrupt me.
So you mean degeneracies with the random VP?
Yeah. Yes, absolutely. Well, first you see, for instance, let's imagine, okay, this one, no. So let's imagine a placket which I can flip, but for which there is no other flippable placket. You see that one? For instance, let's imagine this one, the four neighboring plackets, they have no dimers, which would, well, that's not the case here. I'm sorry to say that, but imagine you can flip a placket and that does not change energy because there are no further flippable placket nearby in whichever position that is. Like a cross thing, right? In that case, you have this degree of freedom, which is two possibilities, which is degenerate. And you can have many of such packets, actually. In principle, I think you can have an exponential. There are some statistical mechanics problem involved in it, but I'm not sure it is known what the answer of that. It's not so important for the rest, but I'm just pointing that very often when you have strong disorder, the model is trivial. For instance, for spin chains, here it's not the case. Okay, we will not explore that limit. We will stay, of course, at finite V, even though it will, as we will see, we will have some large V's. So what we do is just brute force numerics. I'm sorry, no clever things here. We just have a big computer and we use it, and we are able to go to 52 sites on the square lattice and 78 on the honeycomb. And that by that I mean we look at states right in the middle of the spectrum. Okay, so as usual, I will show a bunch of numerics now, which will be about the usual things we do when we have a new model and we want to try to see if there is MBF. So the first thing which everybody does, I'm also doing that. I'm not sure it's a good idea, but nevertheless, we can look at spectral statistics. As usual, we define the gaps like this, the level spacing, and we look if they follow some well-known distribution, like the Wigner-Dyson distribution. This is a probability of having a gap S as a function of S. We did some, we flattened the spectrum. I forgot the name, sorry. And we do that as a function of disorder, like this. And we see if the disorder is small, like 5, we have a nice adherence to the Wigner-Dyson law. And if we increase disorder, we see some zero gap showing up eventually to reach a Poisson limit at large, very large. So another trick which does not need to do the flattening of the spectrum is to use a standard ratio of consecutive gaps defined this way, where we know that we can study the full distribution of error or just look at the mean value, and we know that two well-defined limit. Here are some results for the square lattice, and you see the disorder is small enough, and this is disorder here. We do have a very good adherence to the random matrix ETH kind of value, and if we crank up disorder at some point, and here is a zoom here on the large disorder value, we go towards the Poisson limit. different sample size, which we can do for the square lattice or rectangular lattice. There is some things which move with system size. But if you look here, the crossing is fine. So I don't know if we learn a lot about that, but it seems that it's a transition, not some, maybe not transition, but it's a regime where localized things look localized. If you look at the actual value of the mean gap ratio, it's much lower than what you have for standard MBL in one dimension. So if it's going to be local, if it's going to be in the end transition point, it's much closer to be a localized one than in one dimension, which is not a surprise. That's also the case for the Anderson localization in some sense. Okay, so good for spectral statistics, but we have the eigenstate, so we can look at some entanglement property, which we know there's a very strong difference between ETH and many-body localized, because here as a result as a function of disorder, you will also immediately see two types of regime. One at low disorder, where the entanglement entropy of eigenstate actually scale as a volume. So here I'm taking a R system curve like that, where A is R for the system. And that's typical of the volume law scaling is typical of ETH, where if we look at the strong disorder part, here I have a zoom. Now I'm trying to scale things not with the volume, but with the area, which is like this boundary here, this line here. The scaling is not perfect, but it seems that fairly reasonably starting around value of V equal 20 on the square lattice, that's about the same, even those are less system size in here. We have a reasonable area law scaling for the entanglement. I don't know if I have time for some small intermezzo. I know some of you are interested in entanglement in a constraint system, so let me just show you something funny, which is unrelated to the MBL, but just talking about actually the ETH here. So it's not a big deal, but something which we are trying to finish. So as said that in the low disorder limit, there's some kind of volume law for the entanglement entropy of eigenstate. But if you think about it, when you look at a random state or infinite temperature thermal density matrix and you do the reduced density matrix, if you look at constraint systems, there are some subtleties actually, because it's not a full diagonal, right, for the reduced density matrix. What we find is that indeed we have a volume law. If we just take a, let's say, random state or some infinite temperature density matrix, we have a volume law, but we find that we have a non-trivial correction, which is actually an area law one. It's a positive B. And also, something funny, we think there is some universal constant here, which depends on which type of entropy you are looking at, but yeah. So usually you don't have this kind of B and C. Well, maybe C, maybe you can have, but usually we don't have B. It's kind of easy to know. Once you know it, it's almost trivial to see that if you have a constraint system, well, if you have a constraint, you know, if you, by tracing in A, you do not allow all possible, well, not all possible configuration of A are compatible with that of B, in which means that you know a lot. Which is why, and you know that you know a lot of information on B by just looking at that line. And you have some kind of something which scales with the system size here, information. So that's because actually there are blocks in the reduced density matrix, which and there's an exponential with the area, which makes up for this constant. So it's kind of just a fun, but I just wanted to mention that. What actually is more interesting is probably this universal constant in this model. And that we can recover with numerics and fairly large systems. So that's just a small aparté. If you have questions, I will be happy to discuss that later. So let's go back to MBL. So far we have spectral statistics, we have entanglement entropy. We can do a bit more. We can look not only at the expectation value, mean value of entanglement entropy, but you can look at the full distribution. In particular, it has been realized in one dimension that if you look at the variance of the entanglement entropy, variance with respect to disorderization, different type of eigenstates, and also you can also play with a cut, which we didn't do here. You see that typically you have a signal of the transition, perhaps in 1D at least it's a true transition, I think. Also in the standard deviation or the variance of the entanglement entropy. In particular, you see that there is a peak here both on the square on the Honeycomb lattice if you look at the standard deviation of the entanglement entropy distribution here. And the peak moves a little bit, but it is often interpreted as a signal, pre-signal of something going on. And indeed, it seems to scale, and I will discuss that in more detail later, as possibly a signal of the phase transition, if there is a phase transition. We looked at variance of entanglement entropy. You can also look at the spectrum of entanglement entropy, entanglement spectrum if you want. Sorry, spectrum of the reduced density matrix. Here's a distribution. What we find is a very sharp distribution like that for a small disorder. This is on the square lattice, but we have essentially identical results for the Honeycomb lattice. If the disorder is small, this is exactly what we expect for the distribution of entanglement and eigenvalues of the reduced density matrix. It's much broader. If you look, of course, at strong disorder, this is also typical of MBL. And if we actually scale with system size, the largest eigenvalues of the reduced density matrix, which is done in this inset here, is actually a fairly good power law. And that's something that I think Zlatko was one of the first to see. This is exactly what also is expected and found in a one-dimensional MBL. We seem to have the signal as well here for large enough disorder, which in some sense is very resemblant to what we know from 1D MBL. Okay, so so far we had spectral statistics and entanglement. Now we can look at things which are more closer to experiment. We can just look at local observables, whether they are ETH-like or more MBL-like. So if you want to have an idea of what are the good observable and take a visual inspection of that, here is an example on a fairly large lattice of 52 sites. I just took 3 consecutive eigenstates in the middle of the spectrum, n-1 and n+1, and just look at the expectation value of a bond. That is to say, if I look at the bond, is there a dimer or not? That's very simple to define that. It's a diagonal observable if you want on computational basis. And I did that for the 3 consecutive eigenstates for 3 values of disorder. It does not say much about finite size k and so on. It just to give you a visual impression. If you look at small disorder, basically, and the width of the bonds here is proportional to this expectation value. If you look at small disorder, all bonds essentially have an occupation of 1/4, which is exactly on the square lattice what you expect if you have like a total infinite temperature type of states. That's very standard of ETH. If you now look at large disorder, you see that most of the configuration, and it's different on each of the 3 eigenstates, most of the eigenstates are essentially localized in some sense, close enough, at least from with this observable, comes close to some specific configuration in the basis. Of course, you see some kind of resonance here like that, but just it means it seems to be close, at least visually, to what you expect for single basis states. And now in the intermediate regime, which we believe is close to some perhaps critical value of disorder, it's non-thermal, it's non-1/4 for each bond, and you see there are different patterns here. It's actually closer in some sense to the pattern at large disorder than the one at small disorder. This is just a graphical representation, but of course, now we have to do a bit more work if we want to go into the details of the full distribution of this quantity. And this is what we do here. This is the same thing, but no, not looking just at a snapshot, but just at the full distribution of this bond occupation observable. And this is the same picture essentially emerges than the one from the snapshot. So if you look at the distribution of this B, it has to be 0, 1 if it's a unique dimer configuration. And it's 1 over Z. Z is the coordinates of the lattice. Here, if I'm looking at the Honeycomb Lattice, it's actually 3. It should be 1/3, and this is exactly what we see. The distribution of bond occupation is Gaussian peaked around 1/3 at small disorder. And if you crank up disorder, you will see that you have strong peaks developing at values 0 and 1, which is exactly what we expect if we have a MBL. That's MBL. So we can look.
Can I ask a question?
Yeah.
So maybe you said it and I missed it, but how flippable are these localized states? In the sense, you have a configuration, you can count how many plaquettes you could flip.
I would assume that they are exactly like they are in the basis on average. The bases depend on the lattice, but you can compute that exactly the probability that 2 dimers are nearby are, and that's I would assume that they would be picked around that value.
Because if you don't have disorder, a way to make states which look a little bit localized is just to choose the configurations which are least flippable, which are most staggered as possible, compatible with the winding number.
I would assume, so let me, yes, so I would they be in the middle of the spectrum? Would they have an average of 0? Yes, I guess so, yes. So yes, they could be here, but statistically, they are much less than others, right?
Yeah, of course.
So in the middle of the spectrum, there are maybe some small correlations. I will, if you want, I can show you some plots about what I call the participation entropies, the IPR in more details. But I would assume that the average value is the one of the StatMech problem for this probability that.
Okay, thanks.
Yeah.
Can I also?
Yeah.
Can I also? So there's a question from Srijit. It's on the chat and I will read it out. So it says, will isolated monopoles be localized in the MBL phase?
I Srijit, I didn't know you were there. Isolated monopoles. Let me see. There. Okay, so there is no monomer in this model. We don't allow for them. No, you ask what you're asking if I'm sending a monomer or 2 monomers in that state in the eigenstate, would they be? Well, I'm not so sure it's easy to answer that. What would be the transport? Yeah, I think the transport would just be 0, right? That's just a localized state. I assume. Of course, I'm not explicitly including any mobile degrees of freedom here, but I would assume that if it's many body localized, there's no transport whatsoever. As soon as the inclusion of monomers do not change too much the nature of the problem. So if you just have 2 of them in infinite lattice, I think that will not change. I don't know if does that answer your question?
Yes, thanks.
Okay, thank you very much. Okay, so what I was saying is, okay, I moved too fast. Sorry. So there are some MBL peaks, 1 at 0, 1 at 1. And if you look at the weight, they go towards their values, even though even at the other 50, we don't really go exactly to the expectation of 2/3 and 1/3 that we do. So it's not purely, the snapshot picture of purely basis configuration is not totally correct, actually, but it's a possible picture. We can do the same for other local observable. The one which I'm introducing now, it will be useful for the following. So let me explain. This is if you want the equivalent in this type of dimer problems to the imbalance in the usual spin or cold atom bosonic or particle kind of systems, where basically we can prepare a state, initial state like that. The reference state here The equivalent, if you want, of the nail state for a spin chain would be this columnar configuration like that. And we can cook up a number which is 1 if we are in these states and 0 if we are in a kind of thermal state. That's, yeah, if you want some kind of staggered magnetization. So let's call it imbalance. And we can look at the probability distribution of that imbalance. And what we see on the square lattice here, that we see the same signals. If we are at low disorder, we have a Gaussian around 0 with a very small variance. If we increase disorder, the variance in standard deviation is getting larger and larger. At some point, you see some really very flat. It has to be between -1 and 1, I should have emphasized. It's starting to be very flat, and you can actually see starting around 15 or 20, some peaks develop here. And the more you increase disorder, the more peaks you have, the sharper they are defined. And actually, these peaks, I didn't show that in pictures, they are exactly the one that you expect for basis states. So the peaks are located exactly at the position of the basis state, but you see they are not perfectly delta peaks. You still have a background even at disorder of order 30. So the picture of basis state is correct, but it's just to give us an idea, there's still a background of fluctuation of other states here in the eigenstate, other basis states in the eigenstates. Okay, so far for eigenstates. Let's talk about dynamics. Here we can do a bit better in terms of system size. We can study the Quench Dynamics. So exactly like I said, we start with some specific configuration, which is this columnar state. And the equivalent on the Honeycomb Lattice is this one. It turns out to be the most favorable configuration. That's also something that one was alluding to, which means that it's highly connected by the Hamiltonian. So it means if it has to scramble, it probably will do it fast because, I mean, in some way, it's the most favorable state. So we can do exact dynamics up to system size with 64 sites. We actually can do a bit better now on the square lattice and more than 100 sites on the Honeycomb. And we can do that, something I should emphasize, we can do that in both what we think are the ETH and MBL regimes, which is not always possible with other type of methods. We are not able to go to the infinite time limit for this large lattice size, but we can go to something at least 1,000 placket flips, something like that. So here are the results. If we look at the imbalance dynamics, so this quantity has to be 1 as usual at time 0, and we just follow the dynamics as a Quench. So this is on the square lattice, and this is on the Honeycomb lattice. If we start a small disorder, we have a very rapid relaxation towards 0 after, I don't know, 25 lattice placket flips. We are in thermal state. This is for different system size. And as you expect, if we increase the disorder, things start to be a bit slower. So for instance, for the 32 site, it's almost here, but of course, there's a fine size effect going in that direction. We are not able, unfortunately, to go to a much larger system size. But what I would like to emphasize is that at large disorder, I mean, for fairly large system, it's 64, it's 108. We don't see signal of things going to 0. The imbalance is not thermal even after 1,000 lattice flips or something like that, which is even more better seen on the Honeycomb lattice. Actually, we have some power law. We have a fit to a power law decay here, from which we extract the infinite time value on these lattice sizes. This is not, again, a proof of full localization on an infinitely large system at large system size, but it shows that, and that's at least one of the conclusions we can reach, if we are able to build such a lattice with some experimental technique with 100 sites, we will see for these values of disorder, like the 1 year, we will see localization for almost all purposes, on which typically 1,000 placket flips is typically the time scale which is close to the experiments on bosonic or fermionic degrees of freedom. So there's clearly at large disorder a memory of the initial configuration because the imbalance does not go to 0 and it's actually saturated. Yeah. Another thing which we can look, which is a signal, very strong signal of many ball equalization in 1D, is to look at quench dynamics after a quench of entanglement entropy. Because in one, I will tell you why. So this is again what we do. We start from the initial state, the same configuration, which is a columnar configuration. Of course, that entanglement entropy is 0 because this is just a basis state. So the entanglement entropy at time 0 is always 0. And we look at all things entangled as a function of time. Once again, for the same system size here. Once again, if we go to a small disorder after maybe, as I said, 20 or 30 packet flips, we reach the maximum value of the entanglement entropy. This is a very fast dynamics toward thermal entanglement entropy, which is probably linear here. And if we increase this order, we see that the dynamics is getting slow, but still increases like that. This panel is in a linear scale. Now, if we go to the bottom panels and this panel as well here for the Honeycomb Lattice, they are on log scale on the x-axis, which means we are looking at things as a function of log of t. And we see for the larger system size, we can probe the 64 here, and the 108 here at large disorder. We seem to have something which scales a log t. So if you think about it should, of course, okay, so at low disorders, the entanglement entropy goes to its thermal value, which we expect in ETH phase. And at strong disorder, we see a log growth. This is exactly what happens in 1D as well for the log growth of entanglement in MBL. If you think about it, we should expect actually in 2D rather a log square of t in 2 dimensions. But here I would like to say that the entanglement, the way we do the cuts, our system cut, the entanglement can only grow in one direction. It's not a bubble which grows like that. It just goes in one direction. That's due to the entanglement cut. So which is why, assuming the standard phenomenology of MBL, it's log t as well. Yeah. Okay. So far, I've collected a large number of numerical evidences for perhaps a transition to MBL in 2D, but you might want to argue that this is just a fine system. So what can we really say about that? So let's have a critical discussion. I will be happy to, I've attempted to list the most expected questions from you here, but if you have further one, let me know. Okay, so typical question that I have when I give this talk is, okay, what you see as large disorder is just a big finite size effect. Okay, why not? We can try to probe that. It just may be simply due to the strong difference between an energy scale, which is 1 and 30, and then on finite system, of course, you will see something which it could well be. So that I've done some extra numerics to test this. If you look at the density of states for the different disorderization at large disorder, it's fairly uniform. I mean, it's kind of Gaussian here. There's no bands. And again, from a work from Zlatko, we know that if we have bands like that, it means that maybe we have some finite size effect, and it's just a difference of energy scale that we have to be careful about. This is absolutely not what we see here. Another thing which I've done is to try to look at the dynamics and the entanglement of the eigenstate at infinite time, if you want, for another model which has a large difference of energy scale and a model at the largest disorder. So the black curve are the one which I would assume are MBL. This is the entanglement of eigenstate as a function of system size, and this is the entanglement dynamics. And the other model, the red one, if you want, is a model with a uniform potential plus a very small disorder. So that essentially there's still a factor of 30 between the kinetic part and the potential part. And what we see is that the entanglement entropy is much larger. It goes towards the random state value. It doesn't go to 1. We are still not there on the lattice size, which I can probe. And also for dynamics, we are not yet at the random value, but it's much larger. It's a factor of 3 or 4 in the entanglement, which means it's not that, it's just not a matter of energy scales. Another question I have is the following. Okay, the Hilbert size you simulate in the end, you have this trick of using a constrained model, but in the end, matrix size are the same. And that's totally correct. Indeed. So you probe the same type of level spacing, so what's the point? That's correct. But I would like to argue that we are allowed to probe for more broader range of n. If you do a spin-on-half model on a square lattice, you can do 16, 18, and 20 sites, and that's it. You cannot do 24. There's no 24 on the square lattice, and you will have problem with your exact numerics. Here, we have a larger set of regular sample. We also have rectangular sample, which means that's what I've tried to do. We can probe broader range of lattice size. We can have more. If we have to do fine size scaling with 2 samples, then it's very hard. If we have 6, 7, or 8, it's more likely to see a tendency. Even though, as we will see, it's very hard. So talking about fine size scaling, why don't you try to do, if you assume that there is a fine size phase transition, why don't you try to do fine size scaling, maybe in a continuous fashion, scenario fashion, where you just try to scale everything as a function of L over Xi, where Xi is a localization length, if you want, on the level. That's possible. I didn't dare to do it, because even though I have a broader range of lattice size, I don't have a broader range of linear size, which is different. Also, since I have to play with the shape of sample, you might want to know, some of you know, but how can you imagine a square lattice with 40 sides? That seems a bit strange, but it's possible because I'm playing with some tilting angle. The point is that since I'm using this different aspect ratio, different tilting angles, I also expect that the universal function here should be dependent on the aspect ratios, which means it's probably hard to define size scaling. It turns out anyway that in 1D we have a much broader range of linear sizes. If we do fine size scaling, we still have some issues. I mean, everybody would try to scale the 1D ambient transition, does not find, well, I think so at least with what we have, a critical exponent which satisfies the Iris point. So in 2D, it would be even more difficult. Do I still have 2 minutes? Yeah, that's fine. So the other question I have, okay, is you have some fine size effect. You see the trends here, perhaps in the crossing, even though it doesn't actually drift so much, but some quantities of the phase transition have little drifts. That's the one for gap ratio. Some others are very clear drift. I don't know if you remember the entanglement variance. That's also what we see in 1D. There are really things moving as a function of system size. Why don't you try to scale it and see if you get a fine value for the critical disorder? Exactly like in the work of Dogen. Here's what I can do. This is a critical disorder, fine size critical disorder for different samples as a function of 1 over n, n being the number of sites. Well, here are the square lattice, and here is the honeycomb lattice. Well, I've considered this type of plot a fairly large amount of time, and I don't know. You can try to do a 1 over n scaling of the peak of the variance of the entanglement entropy. It goes around here. You can try to do a fit of this honeycomb data. It goes to 21, which is fairly what I see from other observables like this one here. But can you really believe that? I don't know. For instance, we also try to scale more naively the critical value of well, pseudo-critical of the entanglement maximum, variance maximum for the honeycomb lattice as a function of n. And this is the log, this is the v critical divided by n as a function of n. It seems to be fairly flat. Which means basically in this type of plot, do I believe that this is a straight line to find value, or this is a 1 over x type of line? Well, honestly, nobody can say with this data. I don't want to pretend that I can make this extrapolation, because I actually don't know why 1 over m, actually. There's no justification. There's not even an attempt at doing a scaling theory for the 2D MBL transition. There are many of them in 1D, whether you believe it's a continuous transition, it's a KT transition, a KT modified transition. In 2D, there's nothing to guide me, actually. So I wouldn't know why one of them anyway. And finally, so what is my conclusion? My conclusion is, from my experience of numerics, that all data can be interpreted as evidencing MBL in transition in 2D on fairly large system size. There is no systematic error in the numerics, apart from fine size effects. There's no bias towards entanglement, towards MBL, towards ETH. It's the same. The level of numerical evidence, if I look at the bare data, is very close to what I see in the 1D x-axis pinch. This is more or less the same type of signal. It's slightly closer to a transition point, which is perhaps closer to the MBL, but that's mostly the difference. Of course, that's not a proof MBL in some analysis. I'm limited to the system size, and I don't think it's easy to do much better. But if you think about really physical implementation of such type of models, on fairly large system size, we actually see localization up to 1,500 trips. And that's typically the size, there's no experiment on a cold atom experiment on this type of quantum diamond model or really gauge series. But I would assume that would be the typical lattice sizes and also the typical time scales. And if such an experiment is built, it would see localization. Okay, so here are my conclusions. I think I have 1 minute just to emphasize that there are actually a couple of open questions. And besides the fact that is there a true transition in 2D, one theoretical question, which is maybe not so important, but it bugs my mind for quite some time, is are there local integral of motion in constrained window space? Can we build them? It's very hard, I think. I don't know how to do that. There are many variants which are interesting and possible. I've mentioned that this model has a U1 symmetry, but that's because that's a bipartite lattice. Actually, if you go to a non-bipartite lattice like the Kagome or triangular, you have a Z2 conserved number. So there is room for Z2 topological order being conserved in the excited state. So there is room for 2D MBL with topological order in this family of model. We can play with different variants, and yeah, of course, I cannot resist. Most of you know that, but if you just do this model on a ladder, a two-leg ladder, this is just a PXP model, which has been very well known for you guys. This is exactly the same type of constraint, but here, so it's like a 1D downgrade of the 2D MBL. There are many experimental platforms which have been proposed to emulate QDM. I think Johannes maybe was involved in that type of thing. They are not yet at the stage of being really built, and they are not either being at the stage of being at least that I'm aware of. And adding disorder could be tricky also in this type of platform, but maybe nevertheless, it's a perspective for the future. And with this, I'd like to thank you.
Great, thanks a lot. So do we have any questions for Fabien?
Can I ask one?
Go ahead.
Hi, Fabien.
Hi.
Very nice results. So for the local integrals of motion, can you try numerically to check if these local potential terms are such?
I think the point, if you want to build local integral of motions, maybe you can find one, but you want to build, I'm not even sure. You want to build a basis, the full Hilbert space of operators has to be built around this by this construction. Mm-hmm. And I'm not sure you can do it locally. So maybe, I don't know. I think in 1D, in this type of models, you have this same problem, but you can get away with that. In 2D, I don't know. I can measure local quantities, of course, but building a basis of local operators, I don't know. You see my point?
I mean, in 1D, the proof of that power law entanglement spectrum, which you also have here, is exactly related to this. You know, you have local degrees of freedom around the cut, and then.
I agree, which actually, this is just maybe scratching my head for nothing. Actually, as I said, most of the probe we can see, apart maybe from the entanglement entropy in the ETH phase, but this is not so much MBL. There's no much, if you look at the bare data, you wouldn't know if it comes from a constrained model or unconstrained model, from what I see. So maybe it's just I'm being recording. I don't want to say a bad word in English here, but just probably useless, maybe this remark. But still, maybe it's from a mathematical point of view, it could be interesting to think about it. But maybe not useful to say anything about MBA.
Can I also ask a question then? So, I mean, you showed, for example, that in the MBL phase, let's say we buy it and there is an MBL phase. So you showed that, for example, you showed this cartoon picture where you're showing the localized limit. You have essentially a single configuration in that picture involved in that. So, you know, I understand this is a cartoon picture, and you could, you know, you could look at IPRs or this IQ, I forget what it's called. Have you looked at that? I mean,
yes.
Is it, for example, the case that the eigenstates really are essentially a single configuration? Are they multifractal in this Fock space? Are they?
Can you see my screen? Yes.
Yeah,
my talk was too long, so I had to cut. No, as the eigenstates are not just one single configuration, they are actually multifractal. This is exactly what we see. It's good to have this thing in mind. The multifractal dimension is scaling to 0 as one Planck disorder. It's fairly low, maybe 0.15 or so at large disorder, but it's not 0. So this is exactly what we find here. This is a multifractal. Well, this is a leading term of the multifractal dimension, and you see that the curves here they start to collapse around each other. Exactly what we find in 1D. And,
yeah, so this is very similar to 1D, right? Which is
this is
yeah.
Well, as I said, numerically, this is pretty much what we have in 1D MBL. And I think it also goes as 1/, disorder. So yeah. So for those of you who don't know, we expect in 1D MBL, at least of my feeling, that the multifractal dimension would be 1 up to the in the ergodic phase, then jump to a finite value, which is non-universal, I guess, and then at the transition point, and then goes towards 0, but as 1/, disorder. And this is phenomenologically what we seem to observe here. So this cartoon picture is a bit misleading, maybe, but.
No, but also, I mean, you know, because, okay, we're being recorded, so I should not speculate as wildly as I normally do. But I mean, maybe this is actually a good way to connect this to what is good. Okay, so if you view 1D MBL not as a 1D problem, but as something going on the configuration space of, maybe there is some similarity because.
Yes, if you don't know about.
Well, the connectivity is very different, right? Of the
yeah, it's different, but.
So I mean, even there, it's not obvious you should get this kind of same behavior because the connectivity is different.
Yeah, the connectivity is different. That's correct.
No, but that's very important because.
Yeah, of course. Well, yeah, in 1D and 2D, it's not the same. I mean, that's very clear. It's also
no. I meant connectivity in configuration space because.
Yes. Yeah. Yes, it's well, in 1D you have a number of the average connectivity is scaling with system size with L, and also the same in 2D as L squared, right? So. And
also here the constraints. I mean, you would have thought maybe the role of the constraints is that they sort of go and kill some of the.
Well, the prefactor is smaller. That's what constraints do. In some sense, but
I mean, my speculation here, since I'm being forced to, would have been that just brutally measuring, you know, the connectivity might not be enough. It might be the actual structure of the.
Yeah.
Of the.
Maybe.
But if you're not seeing any indication of any difference, maybe not.
Not major. Only things which really are influenced by the constraint. Like if you do an entanglement cut, you really have something where you have this local physics going on, and there you see something.
Yeah, but that's because I think your measuring is different, right?
Exactly.
So it's not clear if it comes from.
Exactly.
So is there not anything which shows a clear difference between NBL, in 1D versus NBL in this kind of timer?
Not really. But of course, this is finite size systems and so on. So in the end, I don't know if it's just a numerical trick. I think it's only that in the end, to have more broader range of system size. But yeah. Even though this non-locality is a bit strange, yeah.
All right, any other questions? Okay, then I'll stop the recording here, and then